Tutorial 8, Part 2, Phase Transformation Reaction and Microstructure Development. Eutectic reaction consists of one liquid phase changed to two distinct solid phases. And by this way, we can define the eutectic system, which is a homogeneous solid mix of atomic and or chemical species to form a joint supernucleus by striking a unique atomic percentage ratio between the components. And we can define the eutectic composition as the eutectic composition at such eutectic point. And how can we identify the eutectic reaction in a phase diagram? We use the phase diagram example. Here, the first thing we notice that is the line here, is the red line here. When we go down here, you can see that 100% of liquids originally will suddenly change to two distinct solid phases, which is marked by the alpha plus beta in this region. And basically, that's how eutectic reaction defines, and therefore we defined the eutectic point as the point here, marked by my pen. And let's say if the composition have a slightly more alpha phase, and we call it hypoeutectic alloys. In this case, it has less silver, and if it has more silver, or in other words, have a more beta phases in this system, it enters the hyper region of this alloy. Then we call it hypereutectic alloys. And basically, such system containing an eutectic point, we also call it the eutectic system. Microstructure development of eutectic system. What if a liquid state eutectic alloy solidifies? The first thing, at the eutectic point, when it solidifies, the both alpha and beta solid states will solidify at exactly same temperature, where the temperature is the solidus line, horizontal solidus line here, from B to G. At same temperature, therefore, the structure formed will be laminar structure. What if there is slightly more alpha phase or beta phase? That means for hypoeutectic or hypereutectic, then for hypoeutectic, there will be slightly more alpha phase formed, first solidified first when cooling, which we call it primary alpha phase, and the rest alpha phase and beta phase will solidify as solidus line, which is again BG line BG, which is, we call it eutectic alpha and beta, which have a laminar structure. And one description of the structure is here, shown here. Well, the pink region is the alpha phase, and those primary alpha phase is shown here, which is the circle greens. First, they will first solidify it before entering the solidus line. For beta phase or for hypereutectic alloy, it has a very similar thing. You can see in the green line here. First, there will be some primary beta phase in terms of in the shape of the grains, the blue grains, and then it will be the laminar structure, both eutectic alpha and beta phase, after passing through the solidus line. For example, write down the reaction at point F and sketch the microstructure just below point F. The first thing we need to assume is the cooling is uniform. The reaction equation is written here. But how can we know the reaction equation is written in this way? The first thing, we notice that the two regions just above F and just below F. Just above F, we have the following states, these two following states, alpha phase and the liquid phase. And just below point F, we have these two phases, the alpha state and the beta state. And this region is located in the hypoeutatic region. How can we know that it is hypoeutatic? We first identify the eutatic line. Eutatic line, by definition, is here. On the left of the eutatic line, it must be the hypoeutatic region. And therefore, we have the following pictures describing the microstructures after it just below point F. Just below point F, it is around here, and it is completely solidified according to here. And the first solid will be formed is the primary alpha according to the region just above point F. It stays alpha plus L. And when you draw a tie line just at the solidus line, it marks and it indicates that the primary alpha has 8 weight% Ag, and using similar argument, after it passed through the solidus line, we will have the lambda structured eutatic alpha and the eutatic beta. The eutatic alpha will use the same tie line because it is the question specified is just after F passing through, just at a point just below F. That means we still need to draw a tie line to determine the composition, the silver percentage composition of the eutatic alpha and eutatic beta. For eutatic alpha, again, the intersection between the tie line and the silver and the solidus line is 8%. And for eutatic beta, it is here, and it is 92%. And therefore, we have the following descriptions and answers regarding this question. Other reaction types: peritatic, eutectoid, and congruent transformation. For peritatic reaction, the alpha state or one distinct solid state plus one liquid state is changed to another distinct solid state. Eutectoid reaction is alpha solid state is changed to another two distinct solid states. Why is this in eutectoid? Because OID, the oid, is for solids. For eutectic, it is liquid changed to two distinct solid states. But for eutectoid, it is solid changed to another two distinct solid states. Congruent transformation means there is no compositional alterations for any phases in the reaction. For example, 100% solid state is changed to another 100% solid state, or 100 solid state is changed to another 100% liquid states. One example, find eutectic, eutectoid, and congruent reaction, one for each in the following phase diagram. And some of the phases in this phase diagram are unlabeled, and you need to determine by yourself. And here is one possible groups of choice. The congruent transformation is here at this point, because just above this point it is 100% liquid state, but just below this point it is 100% hafnium vanadium 2 here, and which is congruent transformation by definition. For eutectic transformation, it is shown at this point, as it is because just above this point it is completely liquid state, but just below this point this region is unlabeled. How can we know that it is consists of two distinct solid phases? It is because just at the left of this region it is the beta hafnium solid state, and just at the right of this region it is the hafnium vanadium 2 solid phase. And that means here it must be a mixture of beta hafnium and hafnium vanadium 2, and which match with the definition of the eutectic transformation. At this point, it is the eutectoid reaction. Just above this point, it is 100% beta hafnium solid phase. And just below this point, it is also in another region which is unlabeled. But using the argument similar to what I've just mentioned before, to the left of this region, it is the alpha hafnium solid phase. And just at the right of this region, it is the hafnium vanadium 2 phase region, and therefore they are all solids, and by definition this is the eutectoid reaction.